to be the part one of a three-part webinar series where we're going to be talking about different aspects of the design of die castings. So basically, in the introduction, this is a part one. We're going to talk a little bit about what is a die casting and talk about some of the aspects of that. So before I get going, though, let me just give some instructions. This is kind of the screen. Obviously, we're not talking about sales here, but talking about die casting. But the important thing is I wanted to talk about this control panel and just make sure you guys are all familiar with it and introduce it. So here's a blow-up of the control panel. You can push the orange button, and that will minimize it. And then if you then, so minimize it, it kind of looks like that. And then if you maximize it again, then the reason I'm telling you this is that you can answer, or you can input, I should say, questions. And so there's a couple of ways we're going to do this. What we are is we're going to hold the questions until the end. And so I'll be answering any questions you guys have at the end of the webinar. But if you have any questions as we go through on slide 23, something I say is not clear, you can type real time. You can just type there in the bottom where it says enter a question for staff. Just type it in there and push send, and then that will come to me. And as I said, we'll just kind of save them up. The other way to do it is once we finish, again, you can type questions once the webinar's been finished if you want to save your questions till the end. But we're going to answer all the questions at the end of the webinar today. Okay, so let's just talk a little bit about the sponsors. My understanding is that you guys all get a copy of this webinar, and that's brought to you by the die casters kind of shown here on the screen, which is Dayco, who is a zinc die caster, Chicago White Metal, aluminum, magnesium, zinc, Technical Die Casting, aluminum and zinc, Lakeside Casting Solutions, which is zinc, and Similex, which is aluminum, magnesium, and zinc. And one of the things that we're going to emphasize, or I'm going to emphasize during this three-part webinar series, is that very early in the design process, you should be talking to a die caster. And so it'll become clear as we go through the webinar today and over the next couple of weeks why that is. But obviously, these are 5 die casters that are very keen to talk to you. And so you can certainly go and contact them, and they'll be very interested in talking to you. And again, very early in the design process. Another option, and as we'll talk about this a bit later on today, NADCA has a database of die casters throughout the country. And again, an alternative, you can use the NADCA database, look up the local die caster, and then contact them. And then again talk to them about your problems. Okay, so let's just talk a little bit about NADCA. So NADCA is the trade association. NADCA, obviously, a North American Die Casting Association, is a trade association for die casters, people producing die castings. Suppliers, so people who make supplies to the die casting industry, but also consumers of die casting such as yourself. And so the objective of NADCA is quite a number of things, but obviously education, research and development, and then growth of the die casting industry. And so basically, why do we do webinars such as this? So this is obviously fulfilling the goal of education for one of the 3 parts of the membership in terms of consumers of die castings. And so obviously we're going to try and educate you as users so you know how best to utilize die castings. A useful resource that's available from NADCA is the website shown here, diecastingdevelopment.org. This is where most of the information we will talk about today, you can find that. And also in the following couple of webinars over the next couple of weeks. So this information is covered on this website along with a lot of useful information. So in terms of part design, if you've got some questions about exactly how to design parts for the die casting process, the alloys we use, mechanical properties, physical properties, you can get instant support. There's an email address you can email to and get feedback. NADCA standards, we're going to talk about this I think on the next slide, and there's standards that are available from NADCA that you have to have if you're really designing for die castings. As I said, you can find a die caster, there's a database of die casters, and there's also a number of die casting examples. So a great resource for people who are designing for the die casting process. So here's the product specification standards that I talked about here. We have one, the one shown above in green is for conventional die castings, and then the one shown down below in purple are for squeeze casting, semi-solid casting, and high vacuum die casting. And both of them are invaluable if you are designing for die castings. They involve a lot of information useful to people such as yourself. As I said before, alloys, aluminum, magnesium, zinc, mechanical properties, physical properties, dimensional tolerances, what can we actually achieve with the die casting process, how do we build a tool, what should be specified, lots of other materials. So it's highly recommended that you take a look at these standards. You can get either paper copies, which is what I like to be able to flick through them and kind of find the page I'm looking for, or you can get electronic versions where you can do searches. Again, both are available at diecastingdesign.org/publications. Okay, so let's start talking a little bit more about the die casting process. Why should we pick die castings to produce our components? Certainly, die casting is the most modern of the casting processes. It's about 100 years old or so, even so, but compared that to investment casting, for example, which has been around for thousands of years. So some of the advantages of die casting are shown here on the slide. It's a very modern process technology. We use machines that can be computer controlled. We can design very intricate shapes. Net shape casting economics. We're trying to avoid or minimize expensive finishing operations. We can cast pressure tight components. We get a very, very high quality surface finish. We can get a wide range of mechanical properties and very, very high production rates. And again, we'll talk about that as we go on. So die casting generally produces components from three types of alloys: aluminum alloys, magnesium alloys, and zinc alloys. And because of the advantages that we just talked about on the previous slide, die casting has really made its way into a very, very wide range of different markets. Now, automotive, cars, trucks, tends to be the largest market for die castings. There's lots of die castings in an average car, and there's lots of cars produced each year. So that's kind of why die casting tends to dominate the die casting business. But die castings are used in a wide range of other applications. I'm not going to go through this list, but you guys can read the list here. And so a wide range of different applications for die castings. So why should you, as a designer, learn about the die casting process? The reason is that the design of the castings is very critical to the successful application of the die casting process. So it's really important for the designer to understand the die casting process so we can all have a successful application of the part. If the casting is designed well, then the die casting will run better in the casting plant, and that's good for everyone. It's good for the die caster, certainly, but it's also good for you as a customer. You're going to get higher quality parts if it runs better. It's going to run faster, lower levels of scrap, lower rejects, and therefore potentially lower cost also. So I think this quotation that's on this slide, I think, is very, very important from a design point of view. So let's just read it here quickly. So most companies, and this is from Mr. Chowdhury, and talking about design for Six Sigma, and he's saying that most companies spend only 5% of their budget on design, but design typically accounts for 70% of the cost of the product, partially because 80% of the quality problems are unwittingly designed into the product itself. So if a designer knows nothing about die casting, just what he or she learned in college or from designing parts for other processes, they're probably going to design either a simple part or a machine part. And so if you know nothing about die casting, some of the decisions made by you, the designer, maybe you're going to make it easy to draw, easy to machine, but these will most likely not be the right decisions for die casting. So if you use that approach, you're going to often unknowingly design in difficult to cast features just because you don't really understand the die casting process. So the goal here in this three-part webinar series is to discuss exactly what we should be concerned about when designing die castings. Hopefully, you're not going to become experts in 3 hours, but hopefully this will whet your thirst. You can go out and find more information about die casting. You can look at the NADCA design pages, the diecastingdesign.org that I talked about, or go talk to the die casters, and that's where talking to the die caster again becomes very, very important. So to successfully design components for the die casting process, you clearly need to understand the process itself. So that's what we're going to focus on today. We're going to talk about the different die casting processes. We're going to talk about different aspects of process design, and then finish up describing some actual applications of die castings. So first, let's just talk about the die casting process. And when you use the term die casting around the world, it tends to include any metal cast into a metal mold. So it can include gravity processes where we're pouring the metal with gravity. It can be low pressure processes where we're just using very, very low pressures to fill the mold. Or there's a tilt process, a tilt permanent mold process that also is often included in die casting. But here in North America, we tend to make a more careful distinction. Here, die casting is short for high pressure die casting, or sometimes high integrity die casting processes. And so these are different from gravity poured processes, and these are different from low pressure processes where extremely low pressures are used to fill the cavity. So in North America, die casting or high pressure die casting refers to castings produced using some kind of high pressure die casting machine. I'm going to show some pictures in a minute. The liquid metal is injected at very high speed into a reusable steel die, and then we use very high pressures applied at the end of injection. Generally the low end of about 3,000 psi to as high as 20,000 psi is pushed on the metal once a cavity is filled. And when we look at the total market for metal mold casting processes, by far and away the largest part is high pressure die casting. This is based on pound shipped, based on dollar shipped. And one statistic that's kind of thrown around a lot is that of all the aluminum castings produced in North America, 2/3 of them are produced by die casting. So all the other casting processes put together, sand casting, investment casting, permanent mold casting, centrifugal casting, lost foam casting, all those together make up 1/3 of the market for aluminum shaped castings. 2/3 are produced by die casting. So die casting is obviously a very, very popular process, and we'll talk about that, why it is that at the end. But NADCA, the point of this slide, NADCA is just focusing on the high pressure processes. So as we just talked about, when we talk about die casting, we're talking about castings produced in a die casting machine, and it's a large, complicated, hydraulically and electrically controlled machine. I'm showing a picture of a machine on the right. And so generally, we use this high pressure to force the liquid metal at high speeds, at high pressures, into reusable steel molds. And so the picture on the right is a Buehler-Prince die casting machine. I believe it's about a 900-ton machine. And what do we mean by 900 tons? So 900 tons refers to the clamping capacity of the machine. This is the load, the force that we apply to the dies, to the steel dies, to keep them clamped closed as we're injecting the metal into the steel die. Because of the aggressive technique we use to inject the metal, we have to apply very, very high loads to make sure the dies remain closed. And for this, we're using 900 tons, which is about a medium-sized die casting machine. Okay, so this schematic kind of shows the die casting process. This is actually the cold chamber die casting process, and I'll talk about what that means on the next slide, I believe. Anyway, so in stage one, we have the dies clamped closed. Maybe we're applying the 900 tons or whatever clamping load to those dies. And then we have this horizontal sleeve, and we ladle liquid metal into the sleeve. and we can either do that by hand or more commonly these days, we have an automatic labeling machine. Then the plunger moves forward, and it's hydraulically operated, and it moves forward under very closely controlled conditions, and we inject the metal into the cavity. And so the die cavity is shown here. This is where the metal is being injected into. And then as the metal is solidifying, we continue to press forward with that plunger to apply pressure, and the idea is to reduce the amount of porosity in the castings. Once the casting is solidified, the die opens, the blue side of the die moves back, ejector pins, steel ejector pins, push the casting out of the cavity so it's available for either a robot or a pick-and-place device to go in and grab the casting. Then in the fourth stage, we spray a water-based organic lubricant on the die face. This is basically a parting agent to prevent the liquid metal from sticking to the die. Then we clamp the die closed and repeat the process. So as I alluded to on the previous slide, there's actually two major categories of die casting. There's what's called cold chamber die casting. That's shown on the schematic at the top here. And then we've got hot chamber die casting. This is shown on the bottom. And so this slide kind of shows the difference between the two processes. So let's talk about the cold chamber processes. That's the one we reviewed on the previous slide. So again, we have this large diameter cylinder, somewhere between 3 and 6 inches inside diameter. That's called either a shot sleeve. Sometimes it's referred to as a cold chamber, which is where the name comes from. And we pour the liquid metal, as we showed on the previous schematic. We pour the metal through a hole into the shot sleeve, and then this hydraulically activated plunger moves forward to inject the liquid metal under very closely controlled conditions into the die cavity. And so the die cavity is shown here in this schematic. However, with some alloys, those that are melted at low temperatures, such as most of the zinc alloys and some magnesium alloys, we can actually take this whole injection system, the hydraulic injection system, and we can immerse, at least the metals parts of it, immerse them into the liquid metal in the furnace. And so that's what we're showing here on the bottom. Instead of having this horizontal injection, we've now taken that injection system and we've immersed it into the liquid zinc or the liquid magnesium. And so now the plunger operates downwards and it pushes the metal through what's called a gooseneck, through a nozzle, and then into the die cavity that way. And this is called the hot chamber process, and it's called hot as the injection system is in the hot liquid metal. And so the hot chamber process has got several advantages. We don't lose heat in the injection system as we would do with pouring metal into that cold chamber, and it also allows us to better fill thin wall castings, and also tends to be faster. But the problem is that hot chamber can't be used for some of the die casting alloys. For example, aluminum alloys. Liquid aluminum is very, very aggressive, and so it would dissolve this ferrous injection system if we immersed it into a bath of liquid aluminum, as we're showing here for the hot chamber process. So for aluminum alloys and some other alloys that we'll define in a minute, we have to use the cold chamber process. Now there is a slight variation on the hot chamber process, and that's the miniature 4-slide machines. And so here we're showing kind of an example of a miniature machine. Again, this is a hot chamber process. The injection system is still immersed in a bath of liquid metal, but in this example we inject the metal from the back side of the page, and then we eject the castings on the front side out of your screen. So instead of having two die halves that open and close as we've shown in the previous slides, in this case we have four parts to the die. So we've got one part here on the bottom, one part on the left, and one part on the right. And so we have these 4 slides that bring these 4 die pieces together. And there's many advantages of this process because it runs very, very quickly, but generally it only makes small parts. Parts generally the size of your pinky or less. But regarding speed, I've seen one of these types of 4-slide machines making castings every 2 seconds. And so the obvious advantage when we're making high volume parts. So an example is a headphone jack for an iPhone. That's a die-cast component made in a hot chamber miniature 4-slide machine, and obviously a lot of these castings are made around the world. Okay, so let's just talk a little bit about the cold chamber process. This shows the alloys that can be cast in the cold chamber process. So as I said before, all aluminum-based alloys are cast in the cold chamber process, and the reason is that the molten aluminum, as we just talked about, it's very, very aggressive, and if we put a ferrous-based sleeve into this molten aluminum, the aluminum would quickly dissolve it away. So instead we use the shot sleeve or the cold chamber, because the molten aluminum is only in contact with the sleeve for a very short amount of time. Also, then we can use some limited zinc alloys with the cold chamber process. I should say we have to use the cold chamber process for some of these zinc alloys. ZA12, ZA27. These have got high aluminum concentrations. They're zinc-based alloys, but they have quite high aluminum concentrations. The number in the alloy name, the 12 or the 27, refers to the aluminum concentration of the alloy. So ZA12 contains 12% aluminum, ZA27 has got 27% aluminum. So there's enough aluminum in these zinc-based alloys that we have to worry about dissolution of the iron-based injection system with the hot chamber process. So instead, we use the cold chamber process with these alloys. Then there's also some magnesium castings have to be produced using the cold chamber process. These tends to be the bigger castings. So for example, the dashboard of a car is often a one-piece magnesium die casting, and there aren't hot chamber machines big enough to produce that, and so it's produced in a cold chamber machine. And by far and away, the majority of all die castings are produced in cold chamber. So across the industry, it's probably something like 80% cold chamber and 20% hot chamber. And the advantage is, as we can see on the screen, large complex parts. We can use higher pressures, which tend to minimize porosity more, and we can more production layouts possible. Okay, so let's move on to the other process. What are the advantages of the hot chamber die casting process? Well, certainly the alloys we just talked about. We can produce most zinc alloys, such as the Zamac alloys, and we can also produce ZA8. ZA8, as we now know, obviously has 8% aluminum in it, and so that's a lower enough aluminum concentration that it doesn't cause a problem with dissolution of the gooseneck, the ferrous-based injection system. And then also smaller magnesium castings are then produced using the hot chamber process. So the advantage is, we've kind of talked about this, better metal temperature control. We're not pouring into that cold shot sleeve. Automatic refilling. The minute the plunger moves back, it's automatically refilled, and therefore we get less cooling, less oxidation of the metal as we're injecting it into the die cavity. Okay, let's just move on. Let's talk about die casting dies. So this slide shows different types of dies that we actually produce our castings in. So as we go from left to right, the one on the left is a single cavity die. That means single casting. We just produce one component every time we inject the liquid metal into the cavity. The next one over is multiple cavity dies. We can obviously, to get higher throughput, we can produce more than one component per casting. So we can produce lots of components per casting. We can produce 2, 4, 8, 24, maybe as high as 32 if we have very, very small casting. So obviously, that's maximizing throughput on our casting machine. The third one over is a family die. This is when we have 2 or more different castings that are produced in the same shot. And so this is quite nice if we have different parts together, so we can cast the different parts in the same shot, and it allows the die caster to kind of keep them together. And then finally, we have the unit die shown on the right-hand side. This is more interest, I think, to the die caster than to you as a designer, but it allows the caster to quickly switch out specific cavities. It speeds setup time. So maybe, again, you can kind of keep this in mind when you're designing your die castings. Okay, so we pick the process, hot chamber versus cold chamber. We're picking the right machine. We pick the right kind of tool. We know how many cavities we're going to put in the tool. Now we have to pick the right machine for making the castings. So let's talk a little bit about the machines. So a die casting machine can basically be considered to consist of the two separate halves. There's the injection side. This is when we inject the liquid metal into the die, and then there's a clamping side. We have to hold that die closed against these high pressures that are generated during the injection of the metal. So let's talk a little bit about first the injection. That's shown here on the left. It's shown here in red. And this is the method used to inject the liquid metal into the die and create the high pressures. So PQ squared, which is what we're showing here, this is a method used by die casters to decide how big to make the injection system to produce a die casting. And it includes a tremendous amount of information about a number of different parameters that we as die casters need to consider. The maximum hydraulic pressure of the machine, the cylinder size of the machine, the injection cylinder size, the dry shot speed, what's the maximum speed at which the plunger can move when it's unrestrained by liquid metal, the cross-sectional area of the gate or the nozzle, how big is the casting, how fast do I need to fill the casting. So PQ squared is a process used by die casters, and what it does is it allows us to look at all these variables in one simple chart, and that's kind of what we're showing here. So we're not going to go into the details of exactly how this works. That's quite a class on its own. But if you are working with a die caster, ask them about their PQ squared calculations. For example, if you're not sure they're using the correct size machine, ask to look at their PQ squared calculations and have them explain what's going on, because it's a great tool and it allows us to elegantly understand whether or not a machine size will work to produce a casting that you've designed. Okay, so the other half of the machine is the clamping side. And so this is how we size our machines. And we talked about this before. When we have a 900-ton machine, what we mean is that the machine can apply 900 tons of clamping force to keep the die closed when injecting liquid metal into the die. So let's put that in perspective in a minute. Average car is about 2 tons, so 900 tons is 450 cars piled on top of each other. So we're talking large clamping forces, and I said a 900-ton is kind of an average size machine in the die casting business. Why is this important? Because if you don't have enough clamping tonnage, if you don't have enough clamping capacity, what will happen is as we inject the liquid metal into the cavity, this liquid metal will push on the die surfaces and try and force the die open. And if it actually succeeds in doing that, if the machine is too small, doesn't have enough clamping capacity, then it will force the die open, the injection will continue, and then obviously now the liquid metal is going to go everywhere, create a big mess, and potentially a safety hazard. So this shows the method that we use to calculate the clamping tonnage required for a given die casting. And so what we do is that we take the projected area of the shot, as we talk about here on the first line. And what's the projected area of the shot? What that means is that we take the castings, the runners, the gates, the biscuits, and we project anything that we're going to fill with liquid metal onto a single plane on the parting line. And then what we do is that we then multiply that projected area, which is in square inches, for example. We multiply that by the metal pressure, and that's the metal pressure that we're pushing on the liquid metal, and therefore the liquid metal is also pushing back on the faces of the die. And so, for example, we're going to use here 10,000 psi is kind of a common metal pressure used on cold chamber die casting. So let's just run through a quick example. So let's assume we have 100 square inches of castings, of parts, of runners, of gates, of biscuits, that's projected onto the parting line of the die. We're going to apply the 10,000 psi metal pressure to make the castings. We just multiply those together, so that's 100 times 10,000 is 1 million, divide by, maybe that's 500,000. no, it's a million. Divide that by 2,000 because we want to convert from pounds to tons, and that gives us a 500-ton clamping force is required. Generally, as a die caster, you would apply a safety factor to that, maybe 20% bigger. So if that was a calculation, you'd probably run it on a 600-ton die casting machine. So if you know the process that we now need to use to calculate machine sizes, you can run that as a designer to make sure the caster is going to be using the correct machine size. So for example, you run the calculation and the estimate that the machine size is 500 tons, as we just talked about. The caster says he's going to run it on a much smaller machine. Ask them for their analysis. Ask them how they are planning to do that. If they want to run it on a much larger machine, say 2,000 tons, well, that's going to be a little big. It's going to run slower. Again, ask them about their calculation. So when we talk about size of machines, now we need a balance between the two variables we just talked about. We talked about injection capacity. We talked about clamping force. And so we need to make sure both of these are met by the machine that we're planning to run the casting on. Now, do bear in mind, though, that die casting machines from different manufacturers, they can be a little different. One die caster might need a 600-ton machine to make your part. Second die caster might only need a 500-ton machine. So there are a little bit differences, but the differences shouldn't be huge. Okay, so let's move on. Let's talk about some other things that I, as a designer, need to be concerned about. It's not just enough to say that I can inject the metal at the required speed and hold the die closed. There are a number of other things that we all need to be concerned about. So here are the four biggest ones. Number one is filling pattern. How is the liquid metal going to fill the die cavity? Is it going to fill it in a good way? Is it going to fill it in a bad way? Second, venting and vacuum. The die cavity before we fill it with liquid metal is obviously filled with air. If we don't take care to move that air out of the cavity, then we're going to trap it all in the casting, and that's going to significantly increase our porosity level. So we need to get that air out of the cavity so it doesn't become trapped in the casting. How do we do that? We place vents in the die, generally at the extremities of flow, because that's going to be the last part to fill. That's where all the air is going to get pushed to. Or we can apply a vacuum to the die. We can actually suck the air out of the die. Thirdly, thermal control. We need to control the temperature of the die because we want to control the solidification of the casting to optimize casting quality, to maximize productivity, and also maximize the life of the casting tool. It's an expensive tool. We want to make sure it lasts as long as possible. Then finally, dimensional control. Die casting, one of the advantages of die casting is it's capable of producing components with extremely good dimensional tolerances. So we need to kind of be aware which parameters need to be controlled to optimize the dimensional capabilities of the process. Okay, so let's just talk about each one of these in turn. So filling pattern. So one very useful exercise that you as a designer can do when you're looking at your part geometry that you're designing is to evaluate, how am I going to fill my part with liquid metal? How well is it going to fill? So generally what we as die casters want, we want the liquid metal to flow from one side of the casting to the other. If we can achieve this, we're not going to entrap air, and we'll get a nice surface on the casting. So here on the slide, we're kind of looking at different examples, and we can just generate some simple rules. For example, if we look at the B example, which is the top right-hand side, we want to take the shortest path across the casting, because obviously the liquid metal is losing heat quite rapidly as it flows through the die. And so we want to make sure that it fills with a good surface quality. So to do that on the B example, the best way to do that is introduce the liquid metal or gate it, as we say, at the center. So this gives us the shortest route across the casting. If we take a longer path from one side to the other, it's going to be more difficult to fill. It's going to take longer to fill, and therefore potentially have a non-fill or maybe a lower surface quality on our casting. So knowing how the casting needs to fill, you as a designer, you can look at the part design, early in the process and kind of think about how am I going to fill it? How do I want the liquid metal to flow? Now, not only do we have to consider how the liquid metal is going to flow into and through the cavity, for the cold chamber process at least, we have to fill the shot sleeve without entrapping air or minimizing the amount of air we trap at least. So there's two major parts to an injection curve. We've got the slow shot speed, and so what we're looking at here on the left-hand side, we've got a graph showing plunger velocity on the y-axis and plunger position as it moves forward on the x-axis. And you can see we've got two speeds defined. We've got the slow shot speed down here, which is VC, and then we've got the fast speed shown here. So let's focus initially on the slow shot. This is VC. And what we're doing here is that we're trying to fill the sleeve while minimizing the amount of air entrapped. So as we pour the liquid metal into the sleeve, it's not going to be completely filled with liquid metal. There's various reasons why we can't do that. So we have to move the plunger forward to fill it. And then we need to do that obviously first before we can inject the metal into the cavity. But we want to do this without entrapping all the air that's in the top of the cold chamber, in the top of the sleeve. And so on the right-hand side, we're kind of showing a couple of examples what happens if you do it incorrectly. So on the top, we can see what happens. This is when the plunger movement is too slow. Now we're still talking about the slow shot speed here. All we're doing is filling the plunger here. And what happens is the plunger is moving forward from right to left. But the speed that we programmed is too slow. So you can see we've formed a wave here. And what happens is the wave will actually hit the parting line and reflect back. So although the plunger is moving to the left, this wave is actually moving to the right. And you can see we've entrapped air here. And now we're going to mix the liquid metal and the air together in the sleeve. This mixture of air plus metal is what we're going to inject into the cavity. Solidification in the cavity is just going to occur incredibly quickly within a few seconds, and there's no way that air is going to bubble out again. So anything we inject into the cavity is what we're going to ship to the customer. So we don't want to mix that air in there. So we don't want to go too slow, and again, we don't want to go too fast. If we go too fast, then the wave actually breaks, and again, it's pretty clear we're going to get a lot of turbulence and a lot of air entrapment. And again, that's what we're going to inject into the cavity. So we want to make sure that we get it right with both not going too fast and not going too slow. And then the fast speed is then used to actually inject the metal into the cavity. That's the high speed that we use to fill the cavity. And again, there's all sorts of parameters in terms of doing that correctly. Okay, let's move on to the second point, venting and vacuum. As we just talked about, we've got to make sure that we get the air that's pre-existing into the cavity out of the mold cavity as we replace it with liquid metal. We don't want to mix the two of them together. So you can do the best job in the world making sure that you don't trap air in the sleeve, but if you don't make provisions for getting air out of the mold, all is going to be in vain, and we'll trap that cavity air in the casting, producing porosity. So here's kind of one way of calculating the vent size. And so we want the area, the cross-sectional area of the vent is equal to the Q, which is the flow rate of the metal through the gate into the cavity in cubic inches per second. And we divide that by 8,000 inches per second. And 8,000 is about 60% the speed of sound in the cavity. And the reason is we don't want to exceed the speed of sound, so we want to make sure the venting speed stays well below that. If you do exceed the speed of sound with the venting, you can get a shock wave in the same way that a supersonic jet gives you a shock wave, and that's going to cut down on the venting and not allow the air to get out of the cavity. And so we need to make sure that the back pressure of the air in the cavity doesn't build up and get too big. And at the bottom right here, what we're showing here is different vent sizes for a given cavity that someone calculated. And you can see as the vent size, cross-sectional area is going down, then the build-up pressure in the cavity is getting higher. And obviously, once it gets too high, then we're actually going to start to trap the air in the cavity. So if we have a problem with venting, maybe we can't get sufficient cross-sectional area for venting, or we can't place the vents in the optimum locations, which is normally, as I said, the last part of the cavity fill, or maybe we've got some problems with the geometry of the casting tool, we've got a slide in the way, really where we want to be venting, then we can use vacuum in the tool. And when we say vacuum, generally we're referring to high vacuum. And this uses a vacuum system to extract the air from the mold cavity immediately before filling the mold with the liquid metal. And so generally we talk in high vacuum, we're talking about less than 100 millibar air pressure in the cavity, maybe less than 50 millibar in the cavity. And so there's a number of systems out there you can use, one of which is called high QCast. And here's some data on the top right, which is showing the comparing. On the right, we've got just normal die casting. In the middle, we've got normal vacuum die casting. On the left, we've got high vacuum die casting. The top picture shows cross-section through the metal, showing the level of porosity. And the bottom shows the amount of gas trapped. And you can see the gas is coming from different places, from hydrogen and aluminum, from water, from methane, from carbon dioxide, and from nitrogen trapped in the cavity. And so vacuum allows us to produce much higher quality castings. Thermal control. And so we also need to control the thermal aspects of the process. We do that using two methods: internal cooling lines in the steel tool and die spray that we apply to the face of the die each shot. And so on the left here, we've got a temperature time trace, and you can see that we get this kind of spiky up and down behavior, and that's showing each of the injection cycles. So as the liquid metal is injected into the cavity, we reach the maximum, and then as it cools, then we spray the die, that reaches the minimum. But what we can see here is that the average temperature is kind of going up as we start the die casting process, and after a while it will reach a steady state or quasi-steady state where the temperature, the average temperature of the die stays stable or relatively stable. But maybe the temperature is too high, and so maybe we actually want the die to be cooler. Maybe we're seeing some sticking or something like that. And so we can redesign the system so that we can cool the die more, and so we could follow the green curve shown here. Alternatively, maybe the die is running too cold. We're seeing some aspects of the die cast on the die casting surface that we don't like, that looks like the die is running too cold, and then we can shut off some of the water, we can shorten the cycle time, and allow the die to run at a hotter temperature. So die temperature, again, is an important parameter. We just talked about that. We're going to affect the surface quality. We're going to affect surface defects. We're going to affect cycle rate, productivity, and die life. So that's a process parameter that we as die casters need to control. Then finally, let's look at dimensional control. This is a thermally driven thing in terms of minimizing the dimensional tolerance of the casting. This is a nice chart that shows the impact of various parameters, not just on the actual dimensions, but also the spread, the tolerance, or the range of dimensions. And so what this is showing here, so initially we build a cavity, then we heat that cavity, and so it expands. That's the dimension we're actually producing our castings in, so that's when we're injecting the liquid metal into it. But then we eject the casting, and the casting cools down to room temperature. As it cools, it's going to shrink, and so we cool it back down, and then maybe, certainly for zinc castings, there can be some stresses built up that can change the dimensions over time. So this kind of shows the dimensional change during the die casting process, but it also shows the dimensional tolerances increase as we go through the process, and that's especially true if we don't do a good job of controlling the process. So how do you as a designer know what the tolerances should be on a die casting? Again, you go back to the books we talked about at the beginning, the product standard specifications that we discussed earlier. They have data on dimensional tolerances. So this leads us to the next area we want to think about. We've discussed conventional high pressure die casting, but maybe we can't make the quality with conventional high pressure die casting, and we need to look at a modified die casting process that gives us much lower levels of residual porosity or maybe no porosity at all. But if we do think we need that, we need to design up front for these processes. It's really difficult or impossible to change a die from conventional die casting to high vacuum to squeeze casting to semi-solid casting. The processes are just too different. But so that means you have to design up front for these processes, but there's a cost penalty associated with these processes compared to conventional die casting, so you need to make sure you use it. So there's going to be three processes we're just going to talk about here briefly: semi-solid metal casting, squeeze casting, high vacuum die casting, and characteristics are much lower or no porosity, heat treatable castings, and weldable castings. So let's talk about semi-solid casting. Instead of using a fully liquid feed material, we're going to use a material that's about 50% solid and 50% liquid. And so this picture here on the right kind of shows the consistency of the material. So the cylinder is still hard enough to maintain its cylindrical shape, but it's soft enough that you can cut it with a spatula. So we can basically consider it a high viscosity liquid. And that viscous flow allows us to control the flow much easier, so we get less trapped air, less porosity. We're already 50% solid, so we don't have to solidify so long, so we get shorter cycle times. That also gives us increased tool life. But normally we get reduced amount of porosity and improved mechanical properties. That's the main driver for using the process. Disadvantages: you've got a pre-process to produce this microstructure, and there's some cost associated with that. Generally, for all these processes, or certainly for squeeze and semi-solid, we use larger gates, larger runners, and we need to get directional solidification. But here's an example of a part. This is a turbo charger impeller produced by semi-solid casting. It's a fatigue application, very, very important fatigue, and so generally porosity is really bad for fatigue in metal castings, and so a turbocharger has to have good fatigue life, and therefore we produce some by semi-solid casting. This is squeeze casting, the second of the processes, back to fully liquid metal, but instead of injecting it quickly as we would do with conventional die casting, we inject it slowly. Take a few seconds to fill the cavity. That allows us to avoid the turbulence associated with conventional die casting. So here's the squeeze casting machine, here's the dies, the clamping system, but instead of the injection system being horizontal, we place the injection system below the die, so we inject upwards against gravity, and that allows us to better control the filling of the cavity. That's what we're showing here. We got the cavity here. It's a simulation. The red is the liquid metal filling the cavity, and you can see we're filling it gently in a non-turbulent manner. We're not going to mix that liquid metal with the air. We're going to push it out of the die through vents. Then we also get directional solidification. This is a similar simulation, but instead of looking at fill, now we're looking at solidification. And you can see we start to solidify the extremities of the cavity, and we want to solidify it back towards the runner, the gate, and the biscuit. So as we continue to push on it, we can feed and eliminate shrinkage porosity in our castings. Process advantages: basically non-turbulent flow, reduced porosity, improved mechanical properties. Disadvantages: because we're filling slowly, thick walls, we have to go with somewhere between 150 and 2.2 inches. Again, large gates, large runners, we have to get directional solidification. Third process is high vacuum die casting. So this is very similar to conventional die casting. So it's fully liquid, fast fill, but we just suck the air out of the cavity before we fill it with liquid metal. And for high vacuum die casting, it's quite a difficult process. You've got to get down to 100 or 50 millibar pressure in the cavity, and so you've got to design the die again differently than you would do with a conventional die casting die. Okay, in the last few minutes here of the presentation, let's just talk a bit about some applications. Again, you can go to the diecastingdesign.org web page, and you can see some of the applications shown here. And this is kind of what the database page looks like. And so you can do a search, or you can just kind of click on any of these castings shown here, and it'll open it up and give you some information about the casting. But it kind of gives you an idea about what people are doing, and therefore what you ought to be doing as a designer of die castings. Okay, so let's just go through a few examples in the last couple of minutes. So here we have a zinc die casting, ZA8. This is a tag that's used in department stores to keep people from stealing clothes. And so obviously extremely high productivity, somewhere around 100,000 parts every month or so. So here, a second example, this is a power conditioning module chassis. This is for rack-mounted electronic components. Here we can see thin walls. We've got very thin fins in the casting. We've got some small holes. What's interesting about this one is that the die caster that produced this part specializes in building dies very, very quickly, so they were able to build the die in 8 weeks and produce initial castings. Here's a steering knuckle. This is a part produced by one of the high integrity processes. This was squeeze cast for the Jaguar XK, and they did a lot of testing before they went to squeeze casting. They converted it from a forged and a sandcast part, and it was so strong they actually broke the test fixture when they were testing it. So again, moderate weight savings and cost savings. Back to conventional die casting. This is a thrust rod for a BMW X5. Certainly BMW and Audi in Germany have been very aggressive in the use of die casting in cars for weight reduction and for cost reduction. And so here they were able to get a 50% weight reduction by replacing steel parts. And they also consolidated 3 steel parts into a single die casting, and that's one of the advantages. I think we'll talk about that as we go on through the webinar series, either next week or the following week. Next one is a engine bracket, again for a no, I guess this is for a Honda, and then significant weight reduction based on the replacement part, which was a stamped steel fabrication. Again, great consolidation, consolidated 16 parts now into one casting. That's a great application of the die casting process, because you're obviously going to save cost. It costs quite a significant amount to produce the 16 parts, and then you've actually got to put them together, assemble them in some way. Instead, we've just got a single die cast component. And then obviously weight saving too, as we went from steel to aluminum. This is a subframe, again a great application of die casting. It was 40% lighter, 16 parts instead of 48, which gave a 46% reduction in well length, again minimizing assembly costs. This is a shock tower. This is quite a famous application in automotive die casting, around the die casting industry at the moment. Shock tower for a BMW X5, produced by high vacuum die casting, gives you a 40% weight saving, 5 steel parts to 1 die casting. And this is interesting. It was attached to the subframe using self-piercing rivets. You can't do that with conventional die casting, because conventional die castings don't have enough ductility. But again, with these high integrity processes, you can get maybe 50% elongation in the casting, and so you can assemble it in that way. Okay, well, that's all we have for today. Again, I want to thank the sponsors: Dayco, Chicago White Metal, Technical Die Casting, Lakeside Casting Solution, and Similex. And again, I encourage you, and we'll talk about this a lot more as we go forward into the next couple of weeks of this webinar series. I really want to encourage you that one of the most important things you can take away from this 3-part webinar series is go talk to the die casters early. Go get their opinion on your design. I'm sure they will help you and modify the casting to make it more die castable, which, as I said, benefits absolutely everyone in the production scheme of things. Okay, so that's all I wanted to say. We will now go on and talk about questions, and I think Athena will come on the line and tell you, if you haven't done already, how to ask your questions.
I shall. So we're going to open it up for questions. So there's a few ways that you can ask questions. Within your control panel, there's a text box. If you type within the text box and hit submit, we'll get your question in on our end. The next thing that you can do is, if you're calling in on a phone or if you have a microphone set up, you can click that hand icon, and that lets us know that you want to ask your question out loud. We will go ahead and unmute you, and you can do so. Last but not least, please feel free to email us at webinars@diecasting.org. Again, that's webinars@diecasting.org, and I'll send you all a chat with that, with any questions that you might have in regards to the content that was presented today, and we'll get those questions over to Steve so that he can answer them. Also, everybody that was on will receive a copy of the recording of this broadcast, and that will be available within the next couple of days, so you'll get an email about that as well. So with that, I think we're just going to hang on the line and see if any questions come through.
All right, we have a question. What EAU would you require to look at die casting? Units per, what's an EAU? I'm assuming it's kind of units per year or something like that. I'll go on that assumption. Tell me if I'm going on the right assumption. I'm not familiar with EAU, but obviously with die casting, we're talking about a big cost up front for the steel die compared to other manufacturing processes. So it kind of depends upon the casting, but somewhere around 500 parts total life is kind of the bottom line. And again, 500, 1,000, something like that is the kind of the lowest production rate, lowest production numbers that you really want to be kind of looking at. Some die casters do specialize and look at lower numbers than that, but I would think about 500 units is really where you want to be looking at, or greater than 500 units. And obviously in automotive, it goes up to millions of units, and that's really one of the advantages and one of the reasons why die casting is used a lot. But I would say that kind of an area. Estimated annual usage. Thank you. What is the minimum part draft requirement? We will talk, I think we talk about draft as we go into this, but that's where you need that book that I talked about, because draft is quite complicated. We'll talk about drafts on an inside dimension. It's different than a draft on an outside dimension, and it depends upon the height of the wall that we're looking at. And so there's no single answer to that, but NADCA has defined that. And if you go to the product specification standard book that I talked about, there's a section on dimensional control, of which draft is one of them, and it'll kind of tell you for zinc, for aluminum, magnesium, depending upon the type of feature that we're talking about, what the draft can be. And certainly, again, the die caster can help you on that. Often the tool maker will help kind of define what the draft can be, but certainly you as a designer ought to be kind of aware, if there's certain faces that you don't want or want to reduce draft on it, then you need to be clear about that also.
Okay, I don't see any other questions that have come in, but if you're currently in the process of typing a question to us, just click that little hand icon. That'll just let me know that you are in the process of typing and that we should not end early. Okay, I have one hand raised, so we will wait on the line until we get that question in, Gary. Hi, Gary. Are you looking to ask your question? Oh, never mind. It came through in chat.
Oh, what is the tooling cost for office chair base? This is where you need to go talk to the diecaster. I've never produced an office chair base, and so I don't know. But I'm sure any of these guys that's listed here would be very approximately. I don't know. Die-casting dies start at $50,000. I'm going to get killed by people if I'm off here. I would say a die-casting die is $50,000 upwards. For a complex automotive die, it can be more than $1 million. But of course, production costs with die casting are so low compared to other casting processes. Die casting is generally the lowest, for example, in aluminum. I would assume a chair would be aluminum. Generally, aluminum die casting is the lowest cost way to produce a complex 3D shape, such as a chair base. And so for a minimum of 50 units to 1,000 units, 500 units to 1,000 units. So, yeah, I mean, the die cost doesn't really depend upon the number of units being produced. Generally, the dies are all produced in the same way. You would generally produce them all from the same kind of steel. The steel is a minor part of the production costing of a tool. It's the design work and the fabrication that really where most of the cost comes from. So we don't normally, maybe you could for that low production, produce it from a hardened steel tool, which might take 10% off the cost or something like that. But you really ought to go talk to a die caster. I mean, go talk to one of these guys, send them a picture, a 3D drawing of what you got, and ask that question, and then you'll get a much more educated answer than the one I can give you here. So. Wait a minute, we've got more. How can be productive in cost per unit in die casting aluminum? Okay, maybe I answered the question because I don't understand that question. If you still have another question, if I'm not answering your question, drop us another quick note. But hopefully that's kind of talking about what we're talking about here. And obviously it depends upon the, how big, what we're talking about. Good for now, thank you. All right, yeah. Go talk to a die caster and they'll give you a much better number.
All right, I don't see any more questions coming through. So with respect to time, Steve, I want to thank you for presenting. Everybody else, I want to thank you for attending. Please use the link that you used to register for this webinar in order to register for the remaining 2 parts in this series. And we look forward to seeing you guys on the follow-ups for these. So thank you guys and have a great day. Bye.
Thank you very much.